Um, yes, so Robert and everyone in the keynote gave us a very good jump to talk about multimodal data processing. We started way back when we were training our own Nemotron models 2 years ago, and we realized a very big gap in the market in terms of giving scalable, accelerated data processing pipelines that could help you scale and get all of your data in the training methods. What's very important is that we do all of it in open development, all on GitHub, so that it's very easy for you to consume and get started. Um, our talk would be mainly divided into multiple sections. We'll talk about the need for data curation, how important it has become, going over our architecture, doing a couple of deep dives into deduplication, and other bottlenecks that we've seen and used Ray to overcome a lot of it. And then we'll finally talk about a couple of case studies wherein our customers have seen significant benefit of our pipelines. So ChatGPT happened 2 years ago, and slowly and steadily we've seen an array of new set of models that have opened up, a couple of them generating images, videos, audio, and a lot more Omni models till date. What we've seen is that every other model training starts with data, which means you have raw data snippets that you want to initially label, rewrite, rephrase, and make better. In that case, what we've seen is that a lot of them are duplicates, and you would want to just pass along unique tokens. Generally, around 30 to 40% of the data that we've seen forms in the duplicate section of it. And that significantly reduces. So as we do our pipelines, we've seen that around 90 to 95% of it is not so valuable, and you only have to deal with the rest of it when you start training your models. What's important in all of that case scenario is that there are multiple benefits of doing it at scale. Couple of them, you get better accuracy on your models for downstream tasks. You save a lot of money in terms of training and a lot of time, which means faster time to market for your models. But a lot of it comes with a painful load of challenges in terms of how do we scale these pipelines? How do we ensure that the efficacy of data that is being passed along remains high quality? And how do we do it in a very iterative fashion, which is as fast as possible? So here we are solving that for you. We started this when we initially released a bunch of our own models, and we saw that, hey, our research team faces a lot of challenges in terms of getting this data ready and passing it along. So how do we make sure that the community doesn't face the same? We released our open source NeMo Curator software on GitHub, and then we started releasing a lot of this data sets with models completely under the umbrella of Nemotron, which means we release the data that we prepare using NeMo Curator, we release the models which are open and as accessible as you can get, and a lot of it through research papers. We give out a lot of ablation studies and techniques that we've used. What's very important is that while we started with text, but slowly and steadily we've expanded support for different modalities. And that's where Ray came in. So we had to design our architecture in such a way that it is much more modular and reusable, which means you start with a data snippet. It could be a task, which is the smallest unit of data that you pass along different stages. Then you stitch these stages across different composable pipelines, and your data platform could have multiple pipelines based on the modalities you're dealing with. And we've played around with a bunch of executors. We've mainly focused on getting it productionalized on our own research effort called Cosmos Zena. They have a talk tomorrow. I would recommend you guys check it out. And then we've also used a bunch of other Ray libraries, such as Reactpool or Ray Data. Based on the stage and modality, we've played around and found out a bunch of hybrid pipelines that work really well for us. Having said that, we release a ton of canonical pipelines right from text, wherein we start with the data sources, you do a bunch of download and extract, remove a lot of boilerplate, and a lot of rejects and rule-based filters. A lot of it is CPU-based, we found out that a lot of the time that our resource team was spending was CPU-based deduplication back in the day. So we used a lot of rapid libraries to get all of that on GPU. That significantly reduces our wall time and allows you to get any new unique data into your training methods as fast as possible. We've seen that as you move from one modality to the other, which means from text to image, image to video, audio, the scale at which you're dealing with data significantly increases, which means from the early petabytes from text to hundreds of petabytes as you go towards image, video, audio modalities. What's very important is that labeling a text data set is much more simpler, which means you can use a bunch of board-based small classifier models, SLMs, wherein when you're going from text to image, image to video, a lot of it falls down to, for example, VLMs for captioning or generating a bunch of embeddings that then are significantly used for running dedupe and search functions on top of it. All in all, we have a bunch of these getting started guides for you to play and get your data ready across different modalities. Now I'll pass it along to my colleague Ayush, who will walk you over the deep dives.
Hey, so like Aram mentioned, I mainly wanted to go over a couple of sort of use cases where we use these pipelines and talk about why Ray specifically helps us in some of those cases. So the first thing is streaming. Essentially, before we migrated to Ray, we had two options. Either we did batch-style processing, where after every stage, we wrote out a disk and then started the next stage. And obviously, that doesn't scale well if you have, using remote storage, or if you scale up to videos or images, then you're not dealing with terabytes, but rather petabytes of data. And the I/O cost you pay is extremely heavy there. So that's where streaming kind of comes in. What streaming allows us to do is allows us to basically pass in this data from stage to stage and also overlap the compute, especially in heterogeneous cases where we have a mix of both CPU and GPU pipelines. We can kind of overlap both of those together, and that's the main benefit of streaming. Now, Ray Core by itself has all the pieces to enable streaming, but Ray Core itself isn't some sort of streaming engine. So that's where both Cosmos, Xena, and Ray data come in. Aram mentioned that Cosmos Xena has a talk tomorrow. They'll go more in depth on how they handle streaming and some of the scaling things that they built on top of Ray Core. In addition to that, we also have Ray data, which also provides a lot of this. They also allow you to basically stream data between stages. And with the streaming, what we see is in a simple pipeline, which is just tokenization plus inference, just these two stages. The fact that we can overlap the CPU tokenization with the GPU inference, in this case, gave us a 20% improvement. And when you're talking about petabytes of data and these jobs taking weeks to run some sort of embedding generation or run models, 20% is like a big speed up because you're saving in the order of many hours or even days in some case. Now, next thing that was really, really helpful when we moved to Ray is resource allocation. If you're familiar with Ray, you almost take this for granted because it's so easy to do. You just say num CPUs, num GPUs, and things just work. But having used other frameworks in the past, it isn't that straightforward in most other cases. And by being able to specify the heterogeneous resources, as well as being able to specify fractional number of CPUs or GPUs, as well as using more than one GPU in some cases, gives us a lot more flexibility. So if you're familiar with the Ray API, you can typically annotate stuff with the Ray remote decorator and then specify what resources you want. Since Curator kind of wraps around either Xena or Ray data or anything else as an executor, the way we allow you to set resources is the typical way where you have a class and you specify resources being equal to some requirement that you need. The other option is if you already have a class that might have some default resources, you can also override them like you see right at the end, where you instantiate the class, but then you say with resources equal to something else if you want to do that. And typically we use this for many sort of model stages where depending on the model you're using, the resource requirements might be different. So instead of changing the class, you can just set it during runtime. And then the third case where you can actually set resources is if you just have a simple function that you're kind of converting into a stage, you can just use the processing stage decorator and specify the resources there. And one use case where this really helped us is we had a pipeline where previously we were doing everything on the GPU. So we started up a GPU cluster and we had one process per GPU. And what that ended up doing is we ended up underutilizing CPUs in that setup. And one of the stages in that pipeline was actually CPU heavy. And because we only ended up using as many CPUs as processes that were started up, we really weren't utilizing it to the fullest. And because Ray gave us the flexibility to specify different CPU, GPU resources, just that small change got us like a 5x speed up in that particular case. The third thing is auto balancing. I think this goes hand in hand with streaming and resource allocation, but what both Cosmos Zena and Ray data do in addition to streaming is that they look at the throughput of your application at the application layer. And based on that, they decide whether a particular stage needs more resources or less resources depending on the throughput. So for example, if you have a 3-stage pipeline, some of them are fast. The first one is fast, the second one is slow, and the third is somewhere in between. Ideally, you would want to give more compute to the slow stage and lesser compute to the faster stages so that your throughput is kind of optimized and balanced in those cases. Otherwise, if you end up giving more resources to the fast stage, what will end up happening is it'll keep giving more and more batches for you to process, and that'll end up filling the object store. Eventually, the object store will get too full and it'll start spilling, and then the whole pipeline kind of slows down. And on the other end, if your slow stage is kind of being the bottleneck in this pipeline, even if you throw more resources at your last stage, it's not going to change the throughput of the pipeline because you have a bottleneck in between. So Ray data and Zena both gave us this auto balancing that really helped us with the throughput. And what does that mean for us? It means that combining kind of those three concepts, we ended up with a much, much higher GPU utilization and very little idle time. If you look at the graph here, the initial warm-up is basically when some default resources are allocated to every stage. And as the task passes the stage and the auto balancer looks at the throughput of each of the stages, it kind of adjusts the resources and then ends up giving more to where it's needed. And what we end up with is pretty much a 99.5% utilization for most of the job. And pretty much what I described in those previous slides was the foundation for our video processing pipeline. If you look at the pipeline, we have downloading, which is basically getting these video clips. Decoding and splitting is splitting up a large video into smaller logical clips or segments. Once we have those clips, it's then passed through a bunch of different models. So it's just like inference after inference after inference, where you first generate embeddings for that video. And then there are filters like motion filter, static filter. We have a VLM captioning stage. And given the scale of video pipelines and the fact that they're mostly linear, like most clips don't need to look at other clips, these particular sort of techniques really helped scale up the video pipeline. Another pipeline I want to talk about is deduplication. And the reason I want to talk about it is because deduplication is often different than most curation pipelines. Most curation pipelines are generally embarrassingly parallel. You can operate on one batch at a time and kind of process them independently. But deduplication actually requires you having a notion of this complete data set. And there are some stages in the pipeline that actually need all of the previous data to be ready before you can kind of inspect it and try to identify what duplicates exist. So the two main ones that tend to be challenging here is fuzzy deduplication, which often is called like locality sensitive hashing based deduplication, which in the case of text is identifying documents that are similar to each other but not exactly identical. So if you look at the text here, there's like a small difference, jumps over the lazy dog versus jumps over a lazy dog. And then semantic deduplication is like a different approach where once you embed either text, images, or videos, you can look at your data in this embedding space and using clustering techniques kind of figure out what data points are really close to each other. And if they're really close, then they're most likely mean the same thing and they are semantic duplicates of each other. And because these data sets require, or these processes require a notion of a large data set and require often shuffling data between nodes, between GPUs, or some level of data movement, we don't end up using either Zena or Ray data for some chunks of this pipeline, and instead we have a reactor pool executor which spins up reactors manually and kind of handles the life cycle for certain steps in this pipeline. So in the case of deduplication, we basically rewrote the whole pipeline to be on GPUs from the ground up. This means that all of the hashing of the documents happens on GPUs. All of the shuffling of data, which is LSH, where you basically, after hashing the document, classify them into buckets that might have overlapping hashes. So essentially, you're identifying documents that are similar based on some overlap of their hashes. And when you're moving the mapping of this min hash to document or document ID around, the movement GPU to GPU transfers, we do that. That is also GPU accelerated. We end up leveraging UCX, which can in turn use NVLink and InfiniBand for super fast transfers. Once you have these buckets, you can end up in a scenario where, say, documents 1 and 2 are in one bucket and documents 2 and 3 are in another. But essentially what that means is all these 3 documents, 1, 2, and 3, were all duplicates of each other, some overlapping with 1, some overlapping with 3. And what we end up doing is we end up using some sort of graph approach, in this case, connected components. Folks can also use union find. These are like the 2 commonly used ones. And what that does is finds like the overall global set of duplicate documents. So even for connected components, we have a graph-based approach on GPUs that's the library is called CoGraph. And basically under the hood, it uses nickel for communication between GPUs and doing the connected components there. And one thing I wanted to note is even though all of this is like super custom, it was really, really easy to set up with Ray. We set up reactors manually and do the bootstrapping process there where each actor sends out a small message to every other actor with like the comms object. And once we have that, CoGraph or the shuffler can kind of interact at that level without any issues. So it was like pretty seamless to like take that existing infrastructure and move it over to Ray. And this particular pipeline, we've been able to scale up basically to internet scale, which essentially is all of Common Crawl and a few other data sets. I think the largest run we did was roughly 80 to 100 terabytes of fuzzy deduplication. I think that was done on 256 GPUs. You can definitely do it with lesser. But I think the more exciting part is the fact that we can do 8 terabytes of deduplication on a single node. And like some of you might be aware, the moment you go multi-node, the moment you have to scale up to multiple nodes, figure out networking, comms, across those things tend to get more painful to work with, debug, etc. And the fact that on a single node, you can scale up to 8 terabytes, which is roughly 2 snapshots of Common Crawl that's not been deduplicated at all, like not even exact deduplication, means that you can very quickly iterate on stuff. And if you look at the graphs, what we have is our fuzzy deduplication performance before we migrated to Ray, which is back in May, versus what we have now. And across the board, what we have seen is roughly a 1.3 to 1.5x speed up. A lot of it coming from some of the points I mentioned before, being able to use CPUs and reducing the GPU idle time. The other one I want to talk about is semantic deduplication, where the pipeline looks like generating embeddings for all of your data, doing some sort of k-means clustering, and then doing a pairwise similarity computation to see which data points are within similar clusters and how close they are to each other. So this pipeline, I think, ends up using the best of both worlds, where if you think about embedding generation and removing duplicates, those are sort of embarrassingly parallel problems where we can actually leverage streaming. So for those cases, we end up using Gray Data or Xena for those parts of the pipeline. But if you think about clustering specifically, that stage needs all the data to be embedded and ready before you can actually do the clustering stage. So the k-mean step, again, GPU accelerated using cuML and Nickel for comms, we end up starting our own custom actor pool and managing the lifecycle there. And even the pairwise similarity, we end up using Torch tensors for doing that. And that means that end-to-end everything is happening on the GPU. Now, another challenge that we actually found while deduplication is the removal step rather than the identification, because if you think about removal, it's basically taking a corpus of hundreds of terabytes, and then you have like a removal list which is tens of terabytes, or like a few terabytes, and you're essentially doing a left anti-join. So you're basically selecting all the documents from one table that are not in the other. And joins at large scale are a hard problem to solve. Like the amount of time you spend in shuffling and moving and sometimes spilling data is what ends up taking up a lot of compute. So what we ended up doing and what Ray allowed us to do is instead of relying on the original document IDs that came with the data set, we actually generate document IDs on the fly while doing the identification, and we keep a mapping of the input files and what document ID range they have in them. And what that allows us to do is transform this join into a different problem where instead of doing this large join between two tables, when we read the data back in, we can use Parquet filtering to just select. We already know what IDs belong to that particular data set. So we can just use Parquet filtering to select a subset of rows from our removal list and just do like a tiny join within that batch. So that helps us avoid that large data movement and converts this into like a smaller join problem. Future work, there's still some things we need to explore and look at. One of them is resumability. Right now, I think the way we resume is at the application level where the person who's writing the pipeline kind of manually checkpoints or saves the state of what is done and not done. But ideally, this is something the framework could handle automatically. So we're definitely looking at resumability. We're looking at more deployment examples and cases for where you can just deploy in any scale or like other environments with useful guides. We're looking at doing more with stage fusion. Essentially, a pipeline is just a combination of stages. So in theory, if you had I/O, and right after that you had a stage that was on GPUs, we could technically fuse both of those stages and just directly do the I/O with GPUs using cuDF. So that's something we want to explore. And then, as you might have seen in the keynote speech, they announced the GPU object store with RDMA. And I think that's something we want to explore as well, because we have many cases where you're just doing inference one model after the other. So if you already have the tensors on the GPU, you don't need to pay the cost of going back to the CPU object store and then transferring back to the GPU. So these are the main things we're going to focus on. Aram's going to come back and talk about some case studies.
Awesome. Thanks, Ayush. So we've been working with a lot of customers across the board, trying to train models, fine-tune models across different modalities. What's very important in all of these cases is that the challenges remain the same, which means it takes them a lot of time to do data processing today, which we help accelerate across the board, 10 to 30x based on the customer. And then efficacy of the model significantly increases as they adopt our pipelines. What's very important is that we've also seen that compute costs also go down because we've made sure that everything that we've optimized in our canonical pipelines can just apply as they are deploying it on their infra. These are a bunch of resources. You could directly start with our GitHub or documentation, or just pull the container and get coding. Thank you. We would take questions now. So if anyone has a question. Yeah.
So I see you have two backends. One is Ray
Yeah, it's built on top of Ray core. Yeah. So we have three different executors. One is Cosmos Zena, which is built on Ray core. We have one called Reactor Pool, which we are running on dedupe, and then we are also working with the AnyScale team to get more of Ray data into our pipelines. Yeah. So based on the stage, we've optimized which works best right now. Anyone else? Yeah. Yes. The Ray primary library is called Cosmos Zena. They also have a session tomorrow. Definitely check it out. And then all of our pipelines and all of our current Ray code is all open sourced. Yes. Anyone else? Great. Have a good Ray summit. Thank you.